Hello, good evening. We'll wait a minute more. People are still joining. But in the meantime, please let me know if you can hear me clearly and see my screen. Great. Thanks for confirming. Thank you. We'll just wait a minute more. By the way, how are you guys finding the course so far? So we're at week 3 out of 12, so that's already 25% of the course done. So you must have got an idea of what the course is like by now. So just want to get some quick feedback. Do you find it very tough, or is it mostly okay? Anything else you want me to cover in detail? Little tough, okay. Anyone else? It's okay. Okay. Yeah, again, depending on what kind of a background you come from, some of these things may be very straightforward or they might be a little complex. So, hopefully, these live sessions will help you bridge that gap and make the best of this course. Okay, I think we can get started. So, welcome to the week 3 live session. So, let's start off with some of the questions that were asked last week. Again, I've tried to cover as many as possible, but I think there are 2 3 left for the next session. So we'll do that as and when we get time. So first of all, someone asked me about books for CUDA hands-on last week. So what I've done here is I've put together three more popular books that I found that have such hands-on examples. Again, I have not gone through these books in detail, so use your own discretion when you try to find a reference. Also, NVIDIA has a site where they have a list of books on CUDA. So I've also linked that here. So you can use that to also find a more detailed look. But like I said last week, NVIDIA itself has a fairly detailed documentation on CUDA hands-on. So that could be a good source to start out with. And I think I told you guys that I would try and find a computer architecture primer, right? A quick recap from which you can sort of, one second. Okay, so a quick sort of recap from which you can get the prerequisites. I've been searching for that, but I didn't really find anything. So Hennessy Patterson's textbook is a very standard source for computer architecture. So what you can do is, if there are some topics that you don't really understand well, you can look it up there. Another popular textbook that's used in the Indian context is Smriti Sarangi's computer architecture textbook. Both of these could be good enough sources for you to learn about certain topics. I'll do another search this week and see if I find something that's kind of more compact, but so far I haven't found anything, right? So most of them are a full course by itself, and I know most of you wouldn't have the time to do a complete course on computer architecture just to get the prerequisites for this course. So for now, I would suggest looking up particular topics. For instance, if you don't understand caching, feel free to go look up only caching, right? And most of these textbooks will explain it in a fairly self-contained way. So you wouldn't have to know a lot of other things to understand caching. So you can try that out, and if you're still having difficulty in understanding some of those week 0, week 1 kind of topics, please let me know. I'll try to find some other source. So any questions on this? Any other references that you guys are looking for also, please let me know. Okay, if not, let's move to some of the other doubts that people had asked. Yeah, the other thing that you guys had asked was about cache associativity, all the direct map, set associative, fully associative, and kind of understanding what each of those mean. So this is sort of an illustrative example that will help you clarify the concept. And after this, what I would recommend is, after today's live session where we kind of explain these concepts, go back to week 2 or week 1, wherever you had these questions, and if you weren't able to solve them earlier, please try solving them again. So for instance, this how many index bits are needed or how many tag bits are needed. And if you don't understand that still, then let me know. We can also discuss the questions once more. But in the interest of time, for today, what I've done is put in just the explanations of all of these, which we will go through. But I would like you to work out the problems by yourself, ones that we have already discussed, and see if it makes more sense now. Again, as always, I've put in references to the source that I've used to get all of these. So let's start with direct um, cache associativity, right? So there is an analogy that makes this sort of easy to understand, which is a bookshelf analogy, right? So here what we would do is use a bookshelf to illustrate these three strategies: direct mapped, n-way set associative, and fully associative. So direct is the simplest form of cache mapping. So a cache block can go in only one spot in the cache. So it makes the cache block very easy to find, but it's not very flexible about where to put the blocks. So if you have a particular block or a book in this case, it can go into only one spot in the bookshelf. That's what direct map tells you. So the advantage of this is you can find it very easily. Basically think of it as a lookup table, right? So let's say you have a table which tells you this ID and the book, right? And given a book, there is some way of calculating which one it goes into. and there is only one such possibility. So that means it's very easy to find it, but then it's not very flexible about where to put the blocks. For instance, if I give you something like a modulus, let's say the shelf id, or not really the shelf, whatever you call this, right, the slot id is equal to the book id modulus 5, right? So given the book id, it's very easy for me to calculate the slot id. I just do a modulo 5. But let's say I have two books that give me the same answer for this. So, and there may be other slots in the bookshelf that are empty. So in a way, it's kind of inflexible or inefficient. So that is direct mapping. And the tag index offset, I think we have already gone through. So there's nothing different for direct mapping about these fields. So next, let's look at set associative, right? So we'll start with a two-way set associative example. So now think of each slot in the bookshelf. Here a slot used to accommodate one single book. The difference here is that each slot can now accommodate two books, or the cache has sets that can fit some n number of blocks. In this case, that is 2 blocks, and this is what we refer to as two-way set associative. So now what happens, the index is just helps you find the set, and the tag helps you find the block within the set. So basically earlier all you had to do was find the slot ID, and that would automatically give you the book, right? Here what you need to do further, after finding the slot ID, you still need to find sort of the offset within that slot of the book, right? And that's how you use the tag and index blocks. And also notice that in this illustration, the width of the 3 fields are also proportional to the number of bits. For instance, here you will see that the tag is smaller, the index is a little bigger. In the 4-way set associative, you'll notice, so here we are talking about 4 slots, 4 slots, each with 2. So overall you have 8, and here we are talking about 2 slots each with 4. So notice that the tag bit widens here and the index bit shortens, because the index is just needed to find the set. So here you have 4 sets, here you have 2 sets. So this is what happens as you increase the n in the n-way set associative. So this is set associativity. And then finally, fully associative. So here in a sense you don't need an index, because every cache block can go anywhere in the cache. So here you still have this notion of what set it can go into, but here it can go absolutely anywhere. So which means that it's the exact opposite of this direct, right, where you have it's very easy to find a cache block. Here instead it's very difficult to find it, because every tag must be compared when you find the block. But again, it's very flexible, so you can put it just about anywhere. So these are logically the 3 schemes that you can think of. And another meta comment that this illustration has is that all of these are in some form set associativity. And the comment that's given is the direct map cache is a one-way set associative cache, and a fully associative cache of m blocks is an m-way set associative cache. And if you think about this a little bit, you'll find that it makes sense. But basically there are 2 extremes, right? Fully associative and direct map are 2 extremes of the set associative caching strategy. So I think this is all I had about the associativity part. So go through this after the class as well, and if you still find it difficult to solve those questions, let me know and we can see how to simplify it. So this was the question that we discussed last week, I think, and said that we will go through the answer today. So let's quickly go through it just so that you guys can understand better. So you know what is a branch predictor, so I'll skip all of this. So let us assume that the series of outcomes of a particular branch when it was getting executed within a loop is given. Assume that these are the expected outcomes of the specific branch. T T T N T T T T N T T T T N T. T represents taken, NT represents not taken. Assume that the considered branch predictor, let me finish reading this and then I'll look at the question. Assume that the considered branch predictor always predicts predicted not taken. Calculate what is the percentage of mispredictions for the given predictor. So I'll give you a minute to just read through this and maybe even mentally come up with your own answer, and then we'll discuss the answer. Question 1, week 1 session Q1 regarding number of bits in the word field of memory address. Okay, I don't have the list of. Can you tell me a little more about what exactly your doubt is, and then I'll see if I can. Sure. Okay. So I think your confusion comes from the fact that one word equal to 2 bytes. I think there may have been an assumption in the question that one word equal to 1 byte, if I'm not wrong. Again, I don't remember this very well. I'll have to go look at it after today's session. But take a look at the complete question to see if there was such an assumption and if that would help clarify your question. As per the solution, okay, there is another message. But I think you're asking about an assignment question, which again I haven't taken a look at. But was there an assumption? Was the assumption the same in both the assignment question and whatever I discussed? Okay, then I can take a detailed look at it. Yeah, let me do that and come back to you. Okay, let's move to this question. So, a couple of people have said 75%. Yes, the answer is 75%. Let's quickly look at why that is the case. Um, so, here the branch predictor always predicts not taken. So, look at how many times it is right and how many times it is wrong, right? So, this time it is right, here again it is right, here it is right. So, 3 out of 12 times it is correct. If you count the total, you'll notice that this is 12. And here what is asked is the percentage of misprediction. So the percentage of correct prediction is 3 out of 12 and the percentage of misprediction is 9 by 12 or 75%. That's why the answer is D. Any doubts here? And for the doubt that was asked, can you tell me about which question, which in the assignment that was discussed? I think in my live session you said question 1, and in the assignment is it week 1 question 5? or is it week 2 question 5? Because the week 1 question 5 I see is about some branch prediction. Okay, question 7 to 9. No, but in this question it clearly says that assume that the size of each memory word is 16 bits, right? In our question, I think the assumption was each memory word is 1 byte. So the assumptions matter a lot in all of these problems. So you'll have to read those carefully before solving it. Does that help clarify your question? Okay, great. Yeah, glad that you brought it up. Do bring up such questions because others might have also faced these things. But again, in all of these questions, those assumptions matter a lot because the calculations immediately change. So in our question, the assumption was that it's 1 byte. Here it's 16 bits or 2 bytes. And so that will change the answer. Okay, glad we were able to clarify that. Let's move ahead. Yeah, so this you guys said is clear. Another brief question that was asked is, when we talk about a vector in a vector processor, is it really a matrix or a linear vector? Typically, it refers to a linear array or a vector, right? Not a matrix. But again, depending on the architectures of some of these, it may be different. So I would say in the general case, it is a vector. And here is some additional material on vector processors for people who are curious. You can go look that up. Okay, with that, I think we also had one question on GPU memory types. So let's look at that. So this is basically the analog of the CPU memory, right? We discussed basically cache memory, the registers, and then going lower, DRAM, and then storage. Similarly, you also have a GPU memory hierarchy, and I think briefly it was discussed in the lectures as well. So you have local memory for per thread private temporary data, and you have shared memory for low latency access to data shared by threads in the same SN, and global memory is in external DRAM, and this is for data shared by all threads of a computing application. So this is what I think was given in your lecture notes. I've also tried to give you a little more details in this session, and I think these are from the official NVIDIA documentation or something like that. But this much, understanding this much is definitely enough for your coursework itself. This is just some additional this thing that you can probably use to understand better if you're curious. So yeah, so again, this is what the pictorial representation looks like. So again, you have things like global memory, constant memory, and texture memory. And you also have your local memory, shared memory, and registers, right? And this is shown per grid. And the host so again, we have this terminology of host and device starting from, I think this week we are kind of getting used to that. So the device refers to the GPU and the host typically refers to the CPU side. So the host can read or write the global, constant, and texture memory as indicated by these arrows, and every thread can read or write per thread registers, per thread local memory, per block shared memory. So you'll notice that within the grid there are these blocks or thread blocks, and the shared memory is per block. So again, each thread can read or write that shared memory also. And then there is global memory, which is per grid, right? and every thread can also read or write per grid global memory, and constant and texture memory are read only. Like I said, this is all again additional information which you don't need to necessarily know, but if you are curious you can kind of refer to this, and I've given a little more information in this slide which we won't go through, but in case you're curious about what local memory is used for, or what constant memory is used for, what texture memory is used for, these definitions will help you understand that. And this tells you where that memory is, right, whether it's on the chip or off the chip, and again access, whether it's read write, whether it's cached, and then who can access it. So you can go through this offline. We won't spend too much time on this because it's not very necessary from the course perspective. It's just a very detailed GPU memory hierarchy. And again, remember something that I want you to keep in mind is we might be going through certain architectures in the course that are fairly old, right? This is the case with most textbooks and most courses also. They might use some standard architecture, but remember that that architecture might be very, very old. So something that you can do always is to refer to white papers or architecture diagrams of latest architectures. For instance, Ampere is fairly recent. You can look at Ampere and then compare it with something like Fermi, which you learn in the course, and you'll see how many things have changed, right? So you have something called a tensor core, which is not at all there here, and then you have support for a lot more data types, right? Mixed precision, lower, not just FP32 and FP64, but also other different data types. So this is something that that would just help you to not just understand all of this from a standard architecture perspective, but also look at newer architectures and how things have changed there. So you'll notice how different these two look itself, right, initially, while some things may be same. For instance, the shared memory or L1 cache, you'll see that it remains the same, but a lot of other things may have changed. So take a look at architecture diagrams of newer generations as well. That will help you understand more about how these things evolve with time. Okay. Yeah, I think that's all I have the time to cover for today. What we will do next week is on the caching side. I think I still have someone asked me about cache hit, miss, and penalty, and there was also a CPI question that after I explain this, it will probably be easier to understand. So we will go through both of those. And remember, for any questions that I discuss in class, the answer key is whatever is given by NPTEL, right? So even for this question, I think there was some doubt, which is why I want to double check it. I think you guys gave me an answer that was not there in the option. So I will check back before I come to you with that. But for anything that I give you an answer, it is typically aligned with the NPTEL answer key. It's not different. So we are not discussing anything that's different from the official NPTEL answer keys. How to run CUDA programs in Windows? What is the best way to simulate a GPU? GPU simulation, again, there are a bunch of tools, but I'm not very aware of what they are at the moment. I can look up and get back to you. CUDA programs in Windows is again possible. I have not done that of late. I've primarily used Linux, but you can take a look again at NVIDIA guides as to how to use something in Windows versus Linux. I'll also point you to a couple of resources in the next live session that will help you do this. But that is definitely possible. And with regards to simulating a GPU, what particularly are you looking for? That will help me give you a better answer. Why are you trying to simulate a GPU basically? Oh, run the programs given in class. Okay. So what you can do for that is, I think Google Colab lets you use maybe a low-end GPU. So in case you guys haven't tried that out, I think you should try it out. That will help you run things on the cloud. I think they do have a free. Has anyone else used Colab recently to run GPU programs? You can probably confirm. Let me also quickly check. Yeah, I think it's possible. So I'll just link you to the official page for Colab. So you can run things here, I think. That should be okay. And when there is a programming assignment, right? I think there is something in the week 4 or 5 or something like that. The TAs might also give you official instructions on where to run it. So that might also be there. Watch out for that. But in the meantime, I think you can run things on Colab. Let me quickly look. Yeah, I think Collab is a good one to start out with. If you have issues running things there, let me know and then I can tell you. Okay, when to use MPI or OpenMP or CUDA? Again, that's a good question. Let's take it up in the next session. Maybe giving you a few examples will help understand. Okay, what is the relation between high performance computing and GPU? Do both point to the same? Not necessarily. You can have high performance computing running purely on server grade or very powerful CPUs as well, right? So, high performance computing is sort of an application or a domain, just like, let's say, AI, right? Now, both of these can use GPUs to accelerate things, but they do not necessarily mean the same thing. So, I think someone also asked me last week about the use of GPUs in AI. Maybe that's something I didn't make a slide on, but I can briefly talk about it. So, typically, GPUs are used in both training as well as inference, and it's kind of intended as an accelerator, again because of its ability to handle massively parallel computations. uh, it can it can be used very well to perform deep learning computations. Similarly, for certain high performance computing applications also, for instance, maybe something that's very parallel in nature. Again, lot of HPC programs might have that kind of parallelism. GPUs is a good accelerator, but that does not mean that all of HPC uses GPUs or HPC is the same as GPUs. That's a brief answer. I'll also try to put in a slide next week so that you can refer to some of these resources online. Two tutorials provided in week 3, which you're welcome, which explains how to run CUDA on bare metal. Oh, great! Thanks for pointing that out. I haven't gone through week 3 yet. But yeah, for whoever asked that question, this might also help you. Try that out. And if you still face issues, please ask either directly here or on the discussion forum, and then we can see how to resolve those issues. But Collab is also a good starting point if you don't want to run it locally. Okay. So this part we will cover next week, and also I think someone had a question about in the cache field, why is index in the middle, right? This was an interesting question. But I think there is, and last week I was asking about what do you guys think? Is this just a matter of convention, or is there a functional reason behind it as well? So I think I've found some material on that. I'll try to consolidate it and come back to you in the next week. So both of these we will discuss in the next week. So are there any, and whatever questions were asked today also, I will include them for the doubts part next week. Other than this, are there any questions now that assignment solutions also have been released? Are there any doubts or questions so far, maybe in week 1 and week 2, since that was what was released? If there is anything, let me know. Are predictors used in latest GPU? What kind of predictors? Can you be a little more specific? Okay, you're talking about branch prediction here, is it? Yeah, as far as I know, branch predictors are not used in the GPUs, but let me check and get back to you in detail about that. And why that is again because of the architecture of GPUs. I think you will get to the branching part in maybe 1 or 2 weeks from now. But yeah, I'll again address this in the next session. That's a good question. So yeah, typical thing that you should be doing architecture wise is looking at a lot of features on the CPU and asking yourself, is this needed in the GPU, or is this used in the GPU? If so, why? And if not, why not? What is architecturally different that doesn't necessitate this feature? So that's a good practice to really understand the architectural differences. Okay, we will move to the next part. So, discussion forum questions. Again, what I've done is I saw that there were 2 or 3 more questions lately, but I've picked out questions from the initial week 1 or so, and week 1, week 2, and week 3 and week 4. I will again come to them when we talk about that content, because some of you may not have watched the videos, some of you may not be aware of the content. So it makes sense to align these with the NPTEL week contents. So I think this was the only question that uh, was relevant to week 1 and week 2. So this was about the assignment 1, question 3 and question 4. Cycle time for pipeline processor should be max of given times. So I think this was the question. 3, 2, 1, 5 and 4 were the cycles for each of the fetch, decode, execute, memory write back. And the question was, what is the cycle time? So this person was asking that it should be max, which is 5, plus the extra clock cycle latency of zero point 0.4, but 5.4 is not available. I think one of you answered this question saying that this is mentioned as clock cycles and not in seconds, but the options are in seconds, which is correct. So again, units matter a lot. Whenever you calculate numericals, make sure keep writing the units and finally check if the units that you're calculating matches the units in the answer. That will help you figure out things like that. So here, for instance, it's mentioned that every clock cycle takes zero point 0.4 nanoseconds. So what you need to do is 5 into 0.4, which is 2, plus the extra 0.4, which gives you 2.4. So that's the answer. I think this is also straightforward. The point is, if you miss noticing this, then you calculate it wrong. That's why having the units is always helpful as part of your calculation. Okay, I think with that we come to the end of all previous questions. So I'll wait a minute more here in case you have any questions or any doubts in the assignments that solutions were released to so far. Please let me know. I can again go through that and get back to you. Okay, if there are no questions, let's continue with a quick recap of this week. So again, here is your first introduction to CUDA programming. So we looked at things like the program structure, the compilation flow, memory allocation, host to device data transfer, the kernel launch, and things like grids, blocks and threads, and some function declaration keywords. So we'll briefly look at some of these. So broadly, there is again this notion of a host and a device, right? So the host code is meant for the host device or the CPU, and the device code is meant for the GPU. and there may be systems with multiple GPUs also. So that's what you might have heard of, these device to device transfer and things like that. So you may have multiple GPUs, and that's when this becomes relevant. So any C program that you take is a valid CUDA host code because it can run on the CPU. And CUDA programs typically, which have some device code, cannot be compiled by your standard C compiler. They also need NVCC, or the NVIDIA C compiler, to handle the CUDA part of it. And you also have this notion of host memory and device memory. Again, remember that a lot of these things refer to a discrete GPU. By default, when you talk about GPUs, people refer to discrete GPUs. When you talk about integrated GPUs, this notion of host and device memory might be slightly different, because basically it's your same CPU RAM that is shared between the CPU and the GPU. So that is kind of slightly different. So all of these typically will refer to a discrete GPU. So again, this is the memory layout. So you typically have transfers from the host memory to the device memory, and the device memory to the host memory. And CUDA.h is included during compilation. It's again something you need to handle a variety of functions and variables. And typically, as a matter of convention, h underscore something is used to indicate a host variable. And these are mapped to main memory locations, meaning basically your host memory. So I've kept the recap brief today because again we have a bunch of questions to go through. But any other topics that were not clear in the week 3's videos and slides? Okay, if not, let's get started with the problems for today. Which of the following statements is true? A function declared with the keyword device is executed on the host. A function declared with the keyword global is callable from the device. Keyword host is executed on the host. Keyword device is callable from the host. Take a minute to think about it and let me know when you have an answer. C, okay. C, C, okay. Anyone else? We'll wait for a few more seconds. Okay, let's look at the answer. It is C. So why not A, B, and D? So let's do a quick recap, right? So these are your keywords: device, global, and host. And there are two aspects here. One is where can you call such a function from and where is it executed. So if it has a keyword device, it is only callable from the device and it can be executed only on the device. If there is a keyword called global, it's callable from the host, executed on the device. If the keyword is host, then it's executed on the host, callable from the host. So host and device are kind of clear. Both executed and callable is the keyword itself. Global is the only thing that's slightly tricky, which means basically that you can call it from the host, but it will still execute on the device. Now let's go back to this. A function declared with the keyword device is executed on the host. No, we just saw that. Function declared with the keyword device is callable from the host. Again, no. Function declared with the keyword global is callable from the device. Again, no, it's only callable from the host, as you can realize by looking at this. So function declared with the keyword host is executed from the host. That is the correct answer. Any doubts here? Again, a lot of these are just convention based, right? So here in this week, I think we are more looking at the semantics of CUDA and the syntax. So a lot of things will be memory based. It's basically how well you remember the keywords and the API and things like that. Okay, if there are no doubts on this, let's move to the next one. Suppose you want to allocate memory of total size bytes on the GPU device for a float buffer d underscore a. Which of the following options represents the correct function call for achieving the same? You have 4 options. Think about it and let me know. B, okay. B, B, okay. Any other answers? A, okay. Anyone else? Okay, let's look at the answer. It is actually A. So let's first, again, this is from the NVIDIA documentation for CUDA malloc. So what does it do? Allocate memory on the device, which is what we are trying to do here. We are trying to allocate memory of total size on the GPU device for this float buffer. So you can notice that the arguments it takes are void star star device pointer and size. And this is a pointer to the device memory and the requested allocation. So by that um, um, you can see that void star star ampersand dA comma total size is the right answer. Now this is just straightforward from here. But I have a question. So some of you said B, right? Float star star. So why do you think this has, now that I've shown you the answer, why do you think this needs to be void first of all? Also, why is it star star, which means it's a pointer to a pointer? Can you think about that and tell me? We'll maybe discuss it in the next class. But while this is just a convention, right? You just need to know this to answer the question. But going one step beyond that, why does it have to be void and why does it have to be star star? Any ideas or thoughts? It is a generic pointer and then we are using copy host to device. Actually copy the content. Okay, device does not return anything. Okay. Okay, we have a few answers. The rest of you think about it, and some of this is about me giving you answers directly. Some of this is also you thinking about it and you finding out why something is the way it is. And after this course ends, if you have such questions, you will have to search and figure it out by yourself, right? So that's one of the reasons why I answer some of your questions after a week. It gives you some time to think about it and figure it out by yourself, and then we can discuss. So we'll do the same for this one, but hope why A is the answer and not B is clear for now. Let's move to the next question. Suppose you want to copy the elements of a floating point array h underscore a from the CPU host to a floating point buffer d underscore a on the GPU device. The number of elements of the array is 1024. For a system where the size of float is 4 bytes, which of the following options represents the correct CUDA memcopy call? Here are 4 options. Think about it. B, okay. B, any other answers? We'll wait a minute more. B, okay. B, B, Okay, let's look at the answer. It is B. So, yeah, let's look at the function signature first. So again, this is from NVIDIA documentation. CUDA memcopy is the function, and you specify the destination followed by the source followed by count, and count refers to the size in bytes. And then you have a fourth argument kind. We will come back to this. And this here we are trying to copy from uh, the host to the device. So the destination which comes first is the device and the source comes later. And we are told that the array has 1024 elements and it's a float array, right? And the size of a float is 4 bytes. So the size in bytes of this array is 1024 into 4, which is 4096. This is why B is the right answer. Any doubts on this? Okay, if not, let's briefly look at this fifth argument. Kind says type of transfer. So the question here is the option doesn't even have it. So from that perspective, it's clear that this is the answer. But you'll notice that this kind of transfer is not specified here. So out of curiosity, what happens in that case is what we're trying to understand. So you'll see that kind has 0, 1, 2, 3 and 4 as its values. So 0 indicates a host to host copy, host to device is indicated by 1, device to host by 2, device to device is 3, and the default is 4. So when you don't specify it, which is what we are doing here, the default is what is taken. So what happens with the default? The direction of transfer is inferred from the pointer values, and there is a note saying this requires unified virtual addressing. So this is what happens in this case where we don't specify kind. So this is just for our own understanding, not from the perspective of answering this question. Any further doubts on this? So we'll do one more question and then take a break. We're nearing the 7 o'clock mark. Okay, consider the following pointwise multiplication kernel snippet. So the function is called multiply, and I is calculated as block idx.x into block dimension.x plus thread idx.x. C of I is initialized to 0, and then you do an AI star BI and keep adding that to CI. This is your pointwise multiplication kernel. Now this is a question. Suppose a total of 1024 threads are launched for this kernel. The number of elements for each buffer A, B and C are also 1024. What is the total number of floating point operations involved in the compute operation marked in the code? So you'll notice this comment here saying compute operation, which is basically just this line. So the question asks, what is the total number of floating point operations involved in this operation? So basically total number of floating point additions and multiplications. You have 4 options, so you can take 2 or 3 minutes to calculate this. Any answers? I think we earlier also had one question where we discussed how to calculate floating point operations. So the hint here is this, right? You're asked for the total number of floating point additions and multiplications together. Okay, we have one answer, 65,536. Okay. Any other answers? Think about it, take your time. We have enough time. C2048. Okay. Any other answers? I'll give you 1 or 2 minutes more. Take your time and think about this. C2048. Okay, 1024 multiplications plus 1024 additions, 2048. Anyone else? Okay, let's take a look at the answer. It is 2048. So how do we arrive at this? As somebody said, it's simply 1 add plus 1 multiply, and there are 1024 of them. So why are there 1024? Let's think about this. So you're told that there are 1024 elements in A and B, right? And the way you're doing this is by launching 1024 threads. What is each thread going to do? So this code, basically imagine it as something that's being executed by one thread, which is what it is, right? So each thread is going to do this multiplication that you see here and this addition. So every thread is going to do two operations in total, one multiplication, one addition. How many threads do you have? 1024, which coincidentally is also the number of elements. But so that basically gives you the answer. You have 1024 threads, each doing two floating point operations, which gives you 2048 operations. And that's the answer, C. Is this clear now? Any other doubts here before we take a break? Okay, if there are no doubts, let's take a break, 5 minute break now. So it's 7:04. We'll come back at 7:09. I'll keep the call running, but feel free to step away for a quick break. Okay, let's continue. We have a question. Okay, if the number of elements in the buffer is different, let's say 2048, then what happens? That's a good question. So let's think through that. So here, what you're being told in the program is you're using this to compute your what a particular thread is going to do, right? So you'll notice here that each thread processes only one element of CI. That is something that will change if you have 1024 threads but you have 2048 elements. So a simple modification that you could think of is to do is to compute for two elements of C in one given thread. So what will then happen is each thread will do four operations, one for C, two for CI and two for CI plus one, and you will be multiplying basically 4 into number of threads, and number of threads remains the same. Basically it will double, it will go to 4096, which is in accordance with your intuition as well, right? You think that the number of elements in A, B and C double, and the overall floating point operations or the computation also doubles. That's one sanity check or one way of logical reasoning that you can use. So then it would become 4096. Does that help? So what you should basically keep in mind for such questions is the number of threads and the work done per thread. The code will capture what each thread is doing. So that is typically something that's given to you. So all you need to think about is how many threads are there and how much work each thread is doing. You're welcome. Glad it helps. Okay, if there are no further questions on this, let's move to the next one. Okay, let's consider a kernel which takes as an input two 1D input buffers, D underscore A, D underscore B, and produces one-dimensional output buffers, D underscore C. The associated host arrays for each buffer are H underscore A, H underscore B, H underscore C respectively. Assume that the size of each buffer is SZ. Consider the following host code snippet for the same. So there is some code for initializing host arrays which is not given to you. Code for copying input buffers. You have two statements labeled as 1 and 2 with CUDA memcopy and the destination and source left blank. Then you have code to launch a kernel which is not given to you. And finally you have code for copying the output buffers which is labeled 3, and again you have a CUDA memcopy with these two left blank. Now the question is, each of the three lines of code 1 to 3 have two blanks. Pick the correct option from the following. So you have 4 of these options. So I think you will need information from the previous slide. So let me know anytime you want to go to the previous slide. Me. Okay, we have one answer, D. If you need information from the previous slide, just let me know on chat and I can scroll back. Yeah, sure. Okay, we have another answer, D. I'll wait a minute more. I think a bunch of you are still working this out. So think about the previous question we solved, which had the syntax of CUDA memcopy, and that will help you fill both these blanks. And pay attention to what the question says, as in what is the direction of transfer. Are you transferring from host to device? Are you transferring from device to host? Okay, we have one more answer, D. Anyone else? We'll wait a few more seconds and look at the answer. Okay, let's look at the answer. The answer is D, as several of you said. So why is it D? So remember that the convention is destination comma source, right, from the previous slide. So now what are you trying to do here? You're copying the input buffers. So you're copying it from host to device, right, basically. So this is a template for most computations on the GPU. So first you will have a host to device copy, and then you will do some computation on the device memory. Then you'll finally copy back the results from the device to the host memory again, right? This is typically the case for every CUDA program. And you'll also see here that it mentions host to device, and here it mentions device to host. So all you need to do is to fill out the destination and the source. So here you're copying, so your input buffers are your HA, HP, HC, and HD. So you're copying HA to DA. This is your source, this is your destination. You're also copying HP to DB, and that's your second set of things. And finally, after processing, so I think the HD is kind of irrelevant here, because you're processing A and B, and then putting your result to C. So here you'll notice that the copy direction is reversed. It's basically device to host, and so your destination and source will also be different from 1 and 2. So the answer will be HC comma DC. Basically you're copying from device to host. So I think people may have been confused between, let's see, this C and D, but this is why C is not the right answer. So the hint is also the direction or the kind, which was left blank in the previous question, but here that's also given to you. So that would also be a hint for you if you find this very confusing. But that's why the answer is D. So all you need to remember is that it's destination comma source, and try to reason out from where you're copying and to where you're copying for a particular line. Is this clear? I'll wait for a few seconds to see if there are any questions, and then we'll move to the next one. Okay, we'll move to the next one. Recall the vector addition kernel taught in the lecture. Consider the following CUDA thread launch call, vector add, and you're passing two things, 256.1024. Which of the following options is correct? 1024 thread blocks containing 256 threads per block, 256 thread blocks containing 1024 threads per block, total of 1024 threads, total of 256 threads. Think about this. B, okay. B, anyone else? Wait a little longer. Okay, let's take a look at the answer. It is B, as I think all of you said correctly. 256 thread blocks containing 1024 threads per block. So very simply, the first argument is the thread blocks, number of thread blocks, and the second argument is the number of threads per block. So this is incorrect because it basically implies the opposite, and total of this many threads is also wrong, because to get the total number of threads you would have to multiply these two. So this is wrong. Similarly, total of 256 threads is also wrong. So B is the right option. I'll pause here for a few seconds. Those who couldn't figure out the answer, look through it and see if it makes sense to you now, and then we'll move to the next question. Okay, if this is clear, let's move to the next one. Consider the following kernel function calls and statements. So you have three kernels K1, K2, K3 launched with these launch parameters, and you are given a few statements A to F about them. So this is kind of like match the following, right? So you have four options which give you various combinations, saying for instance, for one, A is correct. So you have to check these four options, keeping in mind the kernel launch parameters and these statements. So I think this will take you a while, but I'm happy to give you the time. Take 3 or 4 minutes to go through this and figure out which is the right option. Hope the question is clear to everyone. Okay, we have one answer C. Okay. I'll wait for some more of you to figure out what's the answer. So this is basically like the previous question, but with multiple kernels and multiple statements. So take your time, think through it. Okay, we have one more answer C. 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 Okay. We'll wait for a few more seconds. Anyone else? Okay, let's look at the answer. It is C. So let's just look at C and see if the options match. So kernel 1, the matching statement is F. A total of 131072 threads are launched. So if you multiply these two, you will get this. A quick also sanity check is 8 into 4. The last digit is 2. But you can multiply it and confirm that that is true. So this part matches. Then for 2, the matching statement is A. 16 thread blocks, each containing 1024 threads are launched. That is true. So it's 16 is the number of blocks and 1024 is the number of threads per block. That also matches. And for 3, the matching statement is B, which says total of 4096. So remember, whenever you have statements regarding the total number of threads, you will have to multiply these two. Whenever you have statements about the number of blocks and number of threads per block, remember that the syntax is number of blocks, comma, number of threads per block. So yeah, so we can take a look at some of these to see what's wrong. So 1 with A, it says 16 thread blocks, which itself is wrong because this is 128. So it's easy to rule out this one. Other one says 1E, which says 128 thread blocks, which matches, but each containing 16 threads. So that's also wrong. It's easy to eliminate this out. Then the final one says 1B. So that B says total of 4096. But you'll obviously see that 1024 into 4 itself is 4096. So 1024 into 128 is a lot more than 4096. So this is also wrong. So this is, in that sense, it's why you could get the answer in 1 minute, right? If you had multiple options where the first pair was 1F, then you would have to evaluate all the second pairs too. So in any match the following question, as I'm sure all of you would have already realized, first try out the first pair and see how many you can eliminate and then check for the rest. That's a good way to save time. But hopefully this question is clear and the kernel launch syntax is also clear. I'll pause here so that you can take a look at the answer once more. Let me know if you have any questions and then we'll move to the next one. Okay, if there are no questions, consider the following incomplete kernel code snippet. So the function says vector sub and I equal to dash. So this is basically how you tell it what that thread needs to work on. And the computation reads if I less than n, ci equal to ai minus bi. And so the description says function takes as input two arrays a and b, computes an element wise subtraction, and populates the resultant c. What should be the value of I? So you have four options. You already have one answer saying b, but take a minute to think about this. We have one answer saying A. Okay. Yeah, pay careful attention to the stars and the pluses. That changes what the answer means. Okay, A. A. Anyone else? Okay, let's take a look at the answer. It is A. So it's basically thread idx.x plus block dimension.x star block idx.x. So let's take a quick recap of what was explained in the lectures as well. So you have this notion of multiple blocks and threads within a block, right? So here for instance you have block 0, 1, so on up to n minus 1, and then each block has 256 threads. So now basically what you're trying to do here is to compute a global thread ID in a sense. So the thread ID within each block is basically this number that you see here itself. So for instance, this has a thread ID of 254. Now in block 1 also there is a thread with ID 254. So one way you could refer to this was something like this, 1 comma 254, or a two-dimensional indexing, right? One index for the block and one index for the thread. But let's say you have to come up with the global thread ID. Basically in cases where, like you saw previously, A has 1024 elements. So now you need to assign what a particular thread is going to handle, right? Which element is it going to work on? During things like that, it is useful to compute a global thread ID. So now if I want to compute the global thread ID here, it's basically like saying 0 to 255 here, and then my numbering starts with 256 here and goes on up to 512. So this one would be numbered accordingly, right? 511 or 510, whatever it comes out to be. So how would you calculate this programmatically? So as you can see, the statement is block ID of x, which is this number here. Let's say block 1 in this example, into block dimension.x. Basically, how many threads does a single block have? In this case, that is 256, right? And then plus thread idx.x. That is basically the ID of that thread within its own block. So in this case, that would be 254. And the block idx of x was 1 here. So I'll just write it here so that for completeness sake. So this will give you the global thread ID of 510. So it's basically like kind of unrolling these numbers, but programmatically doing that. So now here if you see the other options, you see thread ID into block dimension on .x, which is incorrect. Block dimension .x plus thread ID of x. This ignores the block ID, so this also doesn't get it right. Here this part says thread idx.x into block dimension plus block ID. This is wrong because this is not the offset. The thread idx is the offset within a particular block. So remember, if you had to derive this logically, what you need to think about it as is the previous number of threads for all the previous blocks plus the local thread ID. So the previous total number of threads would be the block ID, which basically tells you how many previous blocks there are, right? For instance, if I'm using block number 2, it tells me that there are 2 blocks previously that I need to account for, and for each of those blocks I have to add that many number of threads. So that is the block dimension.x. So basically this part will help you cover all the previous blocks. Let's say I'm looking at block 2, right? It will help me cover the total number of threads in blocks 0 and 1, and then I add an offset basically within this block 2 where is that particular thread I'm talking about. That is given by the thread idx.x. So that is logically the way to reason out this, and that way you won't forget it and you won't get confused by just trying to remember it. Hopefully this helps you. So this drawing this picture out can really help you. All you need to know is this notion of blocks and threads within a block, which I think is simple enough to remember. So is this clear now? Any doubts? I'll just pause here. Okay, if there are no doubts, let's move to the next one. Suppose you want to copy a device buffer d underscore c from GPU to a host array h underscore c on the host. Size of the buffer is stored in this variable. Which of the following operations represents the correct call to CUDA memcopy? You have 4 options. Any answers? C, okay. B, okay. B, B, okay. Any other answers? Okay, let's take a look at the answer. It is B. So I noticed that some of you said C. So the reason why it's B and not C is basically a C programming thing, right? So the first, the array name in C is itself its address. It's basically an alias to an address. So you don't have to explicitly do ampersand for an array. So that's the reason it is B. And the CUDA syntax also follows the same thing. So that's why the answer is B. And let's look at the other option. So here the direction is wrong. remember that we are copying from device to host. So the host is the destination, meaning the host should come first. So that automatically eliminates this option. So looking at D further, so uh, yeah, you have host and device correctly, but the kind is wrong. It's given as a copy from host to device, which automatically eliminates that also. Then you have B and C left, and for the reason I just explained, C is wrong and B is the right answer. Hope this is clear. Okay, let's move to the next one. Consider the following kernel specific system variables and the subsequent statements: grid dimension dot x, block dimension dot y, block idx dot y, thread idx dot x, and you have four statements about them. Again, this is a match the following kind of thing. So take your time. I'll give you 2 to 3 minutes to figure out which is the right match. We have one answer A. Okay. Take your time. I think some of you might still be calculating. Okay, A, A. Anyone else? Okay, let's take a look at the answer. It is A. So, why is it A? Let's do a quick recap of these concepts first. So a kernel, when invoked, launches multiple threads in a two-level hierarchy. We already discussed this, right? So these are the launch parameters. So you can basically think of this as a grid of threads to be launched, and that grid is arranged in a hierarchical manner. We already discussed the first parameter is number of blocks, the second is number of threads per blocks, and all blocks contain the same number of threads. This is capped at a max of 1024, and blocks can be numbered as a three-dimensional triplet. So we'll come to this later. So what some of these terms, what do they mean? So grid dimension is basically the number of blocks in your grid. So if you think of a two-dimensional grid, then you can have something like this, right? Where your grid dimension dot x tells you the number of blocks in dimension x, and your grid voice is breaking. Is that for everyone? Okay, then you might try rejoining. Maybe it's an internet issue on your end, but don't worry too much. It's recorded anyway. So even if there's an internet issue, I'm recording it locally, so it should be fine at my end. But please try rejoining. Yeah. So grid dimension dot x refers to number of blocks in the dimension x. Similarly, block dimension refers to the number of threads per block, and block dimension of x will refer to number of threads per block in the dimension x. And if it's a single dimensional thing that we are talking about, block dimension and block dimension dot x will be the same. Further, block idx dot x is block number for a thread, and thread idx dot x is thread number inside a block. So these are the terminology that you need to remember. Now let's start with these options. So again, grid dimension dot x. So the options you have for it are A and D. Number of blocks in dimension x of a multi-dimensional grid is A. Block number for a thread in dimension y. So this is incorrect. So 1 matches with A, number of blocks in the dimension x. So that rules out your option C, but you still have 3 options to consider. Now let's look at 2, block dimension dot y. So options you have are A, B and C. So let's look at all of them. Block dimension dot y, number of blocks in dimension x, which is incorrect. That rules out 2A. Okay, 2A was never in consideration. C and D are the only things in consideration. So B says thread number inside a block in dimension x, and C says number of threads per block in dimension y. So that's correct. Remember, the offset things are these two, right? The other two talk about the number of blocks or the number of threads. So 2C is the correct answer, which eliminates this 2B. You still have 3 options, so you also need to evaluate 3. So 3, your options are B and D. So block idx dot y, B says thread number inside a block in dimension x, and D says block number for a thread in dimension y. So D is the right answer. As I said, these two are offset these things, and block idx refers to the block number and not the thread number, and that's why B is incorrect. So you're left only with option A, which has to be the right answer. But let's also look at 4 and B. Thread idx dot x refers to the thread number inside a block. So that's also correct, making A your correct answer. So again, if you find this confusing, try visualizing this whole grid. Like, try drawing out a grid, try drawing out blocks within them and then threads within them, and then try to mark out these things pictorially, right? That will definitely help you understand. So try it out in one dimension first, and then you can try it out with x and y. Hopefully this is clear. I'll just pause here for a bit before moving to the next question. I think we may have 1 or 2 questions left, so we are within time. Any doubts here? Okay. Let's move on. Consider the following kernel snippet. Kernel 1, I is equal to block idx.x star block dimension.x plus thread idx.x. If I less than n, C is initialized to 0 and you loop for k to 0 to m. C of I plus equal to ai star bi, and this is referred to as the compute operation. Your question now says, given m equal to 128, n equal to 1024, so m and n were these arguments, and a total of 1024 threads being launched for this kernel, what is the total number of floating point operations? Again, floating point operations translates to total number of additions and multiplications pertaining to this operation. You've already looked at this operation. The only thing that changes here is the mn and the number of threads. So think about that and let me know which of these matches it. If you want me to scroll back to the kernel code, I can do that. Just let me know. B, okay. I'll give you another minute. Think about it. So it's very similar to the previous question that we solved. Think about how much work each thread does and how many threads you have. That's all you need to solve this kind of question. Okay, we have one more answer, B. Anyone else? Okay, maybe this is a bit confusing. Let's look at the answer and maybe then it's clear. So the answer is B. So those of you who got it right. So again, like I said, total number of 1024 threads are launched, right? So that's the first part of your answer computation, number of threads. The next thing I said is the work done per thread. Now notice that this was very similar to the previous question, except that, so basically you have to keep in mind that this kernel is the work that every single thread is going to do. So you have the same operation as before, one multiply, one add. So this is two operations. But notice that you are looping around this operation m times, right? So each thread is going to do 2m times operations. So that is your compute per thread, and you're given the value for m. M is given as 128. So all you need to do is 128 into 2 into number of threads, which is 1024, and that will give you option B. So very simple. Remember, work done per thread and number of threads. Everything else is irrelevant. For instance, here n doesn't matter. This is what matters, 1024 threads. And pay attention to the compute. Here the key part is that it's happening in a loop. So this is the work done per thread. Now is this clear? For those of you who didn't answer earlier, is this clear now? Okay, great. So what you need to take away from these questions is the template of how to solve such a question. So each time things like this M, N, the compute, all of that might be different, right? So you need to know this logic of how do you calculate the total number of flops, because the question might change slightly. That's how every year you keep getting new assignment questions and new exam questions, but the underlying logic remains the same. Okay, let's move on to the last question for today. Consider the following kernel snippet. Again, kernel 2 with an M, N, A, B, C, and you have the same I. If I less than N, you compute sine of A of I. Else, if I greater than equal to M and less than N, you compute cosine of B. Else, if I greater than equal to N, you do a sine of AI plus cos of BI. And the question, the kernel takes two arrays A and B of size 1024 and performs the following operations. For the first 256 elements, C of I equal to sine AI, next 512 cos BI, last 256 sine plus cos. And or however this operation is given. Maybe I didn't read it properly. No, I think the operation is given differently, but that's okay. We'll assume the missing braces here. Values of M and N are passed as 256 and 768. The code above has one line which poses a logical error with respect to the specification given above. Which of the following options correspond to that line number? 4, 6, 8 and 12. So go through this and then I can scroll back to the code. Let me know when you want to scroll. Okay, let me go back here. So these are the line numbers. So see if you can figure out which line number has the error. So basically you want the first 256 to fall here, the next 512 to fall here, and the last I think 256 to execute this. Okay, line number 12. Anyone else? I'll give you another minute. By the way, M and N are 256 and 768. Four. Okay. In the interest of time, let's discuss the answer and you can go back and look at it and see if it makes sense to you. So, the answer is option A, which is 4. and it should be I less than m. So again remember, m is passed as 256, n is passed as 768. So, and what you wanted is first 256 element c should be sin ai, but what is done here is I less than n. So first 768 elements are doing this operation, which is wrong. Therefore this line is wrong. And here what happens after 768, which is basically the last 256, sine plus cos, which is what you want, greater than equal to m, less than n, again greater than 256, less than 768. So that will be the next 512, that is going to compute cos. So that is also correct. So these two are correct. This part is wrong because it says I less than n, which does not map with what one wants to do. So the line number that's wrong is 4, and the correction would be I less than m. Is this clear now? Great. Okay, again, I think we're almost out of time. So yeah, this is the one other thing I wanted to briefly tell you. So again, a lot of this course will emphasize on CUDA, and that holds for NVIDIA GPUs, and it makes sense because NVIDIA has the leading market share, right? But remember that there are other platforms and other software stacks too. For instance, AMD GPUs use this software stack called ROCm. There's also OpenCL, which is used especially for heterogeneous compute, right? It can be used on GPUs and CPUs as well. So these are alternatives to CUDA that people also use. I think this course covers OpenCL briefly. So just keep in mind that CUDA is not the only way to do GPU programming. Again, some questions I had, if we had time, is have you used a GPU and have you used any languages? I'm sure most of you have used CUDA, or you've maybe used PyTorch or TensorFlow. You've not even gone to the CUDA level. But this is something to just keep in mind. And since we are out of time, I will stop here. So if you have any doubts that I didn't cover today, please ask me on chat now. I'll stay on the call for another minute or so. If not, thank you so much for joining, and thank you for keeping it interactive and asking your doubts and questions. So see you next week, and thank you.